Welcome on the webinar. And so maybe let's start. And we have here Wojciech and Tomasz Szczepański, who will be present from medical who will be presenting the work here in Sano in the scope of medical imaging and robotics team entitled Learning Beyond Training, Distribution, Geometry, Robust Augmentation, and Conditional Learning in Medical Imaging. So I will let Marek introduce himself and also Tomasz.
Okay, so welcome everyone. Today we have the opportunity to hear from Tomasz about his ongoing PhD work on learning beyond the training distribution. This is the topic of Tomasz PhD. Tomasz is a PhD student in our team in medical imaging and robotics, and soon he's going to graduate from his research. Okay, Tomasz, the floor is yours. I think you can start the presentation, and after the presentation, we will start the discussion.
Good afternoon, everyone. Thank you for the introduction, and I thank you for joining. My name is Tomasz Szczepański, and I'm a PhD candidate affiliated with the Sano Center here in Krakow and also with the Warsaw University of Technology. And today I will be talking about a line of research I've been working throughout my PhD, how we can help deep learning models generalize beyond the data they were trained on, using geometry as the guiding idea. But before I go into the science, a quick word about where Sano is. For those of you joining from abroad, Sano, the Center for Computational Personalized Medicine, is based in Krakow in Poland. And Krakow is a major academic hub, home to numerous universities and higher education institutions, as well as institutes of Polish Academy of Sciences and the growing life science research cluster. So if you are watching this from outside Poland, this talk is coming to you from the historic former capital of Poland, a city with a long academic tradition. And if you have never been to Krakow, you should come because this is a beautiful place. A little about myself. I hold master's degree in computer science from Warsaw University of Technology, as well as a bachelor's in photonics engineering. My master's thesis looked at a different problem than today's presentation, the problem of data bias in chest X-ray datasets used to diagnose COVID-19 patients. But it was the first time I had encountered medical imaging, and I was so fascinated by it that I decided to pursue this field during my PhD. Since then, I've been a PhD student affiliated with Sano, where I'm part of a medical imaging group. My research interests sit at the intersection of medical imaging, multimodal data integration, and geometric approaches to image analysis. I've been fortunate to be supervised by an excellent team throughout my time at Sano. When I joined, I was welcomed and mentored by Dr. Szczepański, who is my also co-promoter and has supported me throughout my entire PhD journey. Within Sano, I was then supervised by Dr. Przemysław Korzeniowski and more recently, Professor and AGH Marek Wodziński, who took over this role. My promoter is Professor Tomasz Szczepański at Warsaw University of Technology and Dr. Szczepański, who is affiliated with Harvard Medical School. Over the course of my PhD, our works has been presented at MICAI and published in Medical Image Analysis. With that background in place, we can now move on to the research. Here's the shape of my talk. I will start with some motivation, why deep learning in medical imaging matters, and what I call generalization challenge about learning beyond distribution, the core problem this entire body of work is trying to address. And I will walk you through 4 studies in order. I think it tells the best story. First, robust data augmentation through a project called TTSNet. Second, conditional learning through a project called Decode. Third, geometry-aware regularization through GPart 3D. And finally, a most recent piece of work called XSplat, which pushes the ideas towards geometry-grounded generation. I will close with conclusions and where I think this research could go next. Throughout, I want to focus less on implementation details, but for those interested, we can return during questions. I will be glad to answer them, and more on the why these problems matter and why geometry turned out to be a useful tool for solving them. Let's start with the basics. Medical images, whether it's CT, CBCT, ultrasound, or X-ray, drive diagnosis and treatment planning across almost every clinical specialty. Traditionally, a lot of that analysis is manual. A radiologist or clinician looks at the scan and makes a judgment based on their training, knowledge, experience, but it's slow. It's costly, and the quality of the outcome depends heavily on who's doing the reading and how one is tired or burnt out. Deep learning offers an obvious opportunity here. It can automate detection, segmentation, and measurement, turning a raw scan into something closer to a clinical decision, more approachable and much faster than a human could do it manually. But here's the catch. And it's the catch that this entire talk will be about. A model is only as useful as its ability to work on patients, scanners, and hospitals it has never seen before. If it only works on the exact conditions it was trained, it's not clinically useful, or at least partially. The gap between what a model has seen and what it will actually face in the real world is where things get interesting. This brings me to what I call the core challenge, and it's the idea that ties this talk. Deep learning works excellent when training data pins down clearly constraints how a model should behave. Trouble is that in medical imaging, it often does not, and it fails in two quite different ways. The first way is that the data is simply too narrow, too small. The image in front of the model generally constrains the answer, but the model has never seen a scanner, a clinic, or a patient quite like this one. So it guesses, it extrapolates, and sometimes it guesses wrong. Scanners change between hospitals, protocols drift, populations differ, and in medical imaging, you usually can't just collect more data to close the gap, because acquiring and annotating scans needs special equipment, clinical experience, and often years of regulatory approval. The second way is more extreme. Sometimes the input is missing the answer entirely. And this is something I will return to when I will talk about XSPLAT, where a single 2D observation, for example, X-ray, is generally insufficient to uniquely determine a full 3D structure. And additional training data cannot fully resolve the limitation if the missing information is not present in the input. These are two ends of the same underlying problem. The data on its own doesn't fully determine how the model should behave. And in both cases, the remedy is the same in spirit. Something beyond the data has to fill the gap. In this work, that something is geometry. What anatomy actually looks like and how the image was physically formed. So how do we actually give a model geometric structure? Throughout this research, I found it useful to think about two kinds of geometry. The first is the geometry of the anatomy being imaged, the shape, the extent, and spatial relationships of structures a model is asked to segment or reconstruct. The second is the geometry of imaging process itself, the physical mechanisms by which a sensor forms an image and by which artifacts specific to the sensor end up in particular places within this image. And over 4 studies, I introduced 2 kinds of geometry at 4 different points in a typical deep learning pipeline. The first study injects geometry into the training data itself through hand-designed augmentation, that's TTSNet. Second, injects it as a conditional signal, conditioning signal level of anatomical relationships. The conditioning signal letting the network learn a structure's own shape, and that's decode. The third injects it into the training objective as a soft regularization term based on population level anatomical relationships, that's JEPWARD. And the fourth, the last one, injects it into the model's representation itself for a generative task, which is XSPLAT. I will walk you through this in order we worked on them because it pictures our story. The first study forced us to hand design geometry out of necessity, and that experience is what motivated research that came after it, an increasing shift from hand designed to learn geometry. But first, we start with our study. This is joint work with Szymon Płotka and colleagues. published in Medical Image Analysis, the real-time placental vessel segmentation in fetoscopic laser surgery for twin-to-twin transfusion syndrome. Twin-to-twin transfusion syndrome, or abbreviated to TTTS, is a rare and serious condition that can occur in monochorionic twin pregnancies, where two twins share a single placenta. It affects a minority of an already rare pregnancy type. The standard treatment is fetoscopic laser surgery. A surgeon inserts a small camera into the womb and uses a laser to find and seal the abnormal blood vessel connections between the twins. Now, here's what makes this such an interesting machine learning problem. No plausible increase in overall healthcare data is ever going to meaningfully grow the amount of surgical video available to train a model on. This just isn't a problem you can solve by collecting more and more and more data, because the underlying condition and the surgical footage that comes with it is inherently scarce. On top of that, surgeons have to identify tiny vessels through a narrow and turbid, constantly moving field of view, and they have to do it across different hospitals with different camera hardware. Some artifacts which are absent in training dataset are present in some of external data. So we need a method that could generalize across institutions from a dataset that realistically is never going to be large. Our approach has two parts. First, we built TTSNet, a lightweight segmentation network with a channel attention mechanism and multi-scale feature fusion, specifically tuned to preserve thin, low-contrast vessel structures that a more generic architecture might miss. But the whole picture of innovation wasn't only the network, it was how we trained it. Real surgical video is full of artifacts. Laser flare of the surgical device, floating particles in the amniotic fluid, and distortions from the fiber optic bundle in the fetoscope. None of this reproduced well by available generic data augmentation, like the kind of random rotations, flips, and color jitter you would normally use. So instead, we modeled each of these artifacts as a physical phenomenon with its own geometry. Laser flare, for example, we modeled as a circular spot with a distance-based intensity fall-off, mimicking how light actually behaves. And particles and fiber bundle defects were built the same way, from a description of how they physically occupy and modulate the image, and how do they form, how dense they are, what shapes do they take. And this is geometry of the acquisition process. And in this first study, it was hand designed. And looking back, this became the starting point. The recognition that geometric knowledge the network couldn't infer on its own had to be supplied to it directly. And how our solution actually performed, we trained and evaluated TTSNet on newly collected datasets spanning 6 fetal medicine centers across Europe, which to our knowledge was at the time the most diverse multi-center dataset assembled for this particular task. The hand-designed augmentations improved mean intersection over union by several points compared to the same network trained without them, and outperformed the previous best method by a comparable margin. Just as importantly, for a surgical setting, the network runs at over 150 frames per second on embedded medical grade hardware. So it's well within requirements for real-time use in the operating room. The takeaway here is two-sided. On one hand, explicitly modeling the physical and geometric formation of an artifact is both valid and effective. And on the other hand, it has to be designed by hand for every new artifact type or every new sample, a sensor with possible defects or any distinct characteristics. And that limitation is exactly what motivated following studies I will walk you through now. And the question about them is, could geometric knowledge about anatomy rather than acquisition be learned instead of hand designed? And we move here to the second study, work together with Michał Grzeszczyk and colleagues, presented at MICAI. Let me decode you, decoder conditioning with tabular data. Segmentation networks are typically trained end-to-end, from images straight to voxel-wise labels. But think about what's implicit in every one of those training samples. Descriptors like a structure's volume, its sphericity, or elongation. All of the geometric information is in the data, but it's simply discarded the moment the loss is computed, especially cross entropy loss, which is pixel-wise. And 3D CBCT tooth segmentation makes the cost of annotations and creating the labels really striking. Publicly available annotated data in this space are still small and are drawn most from a single acquisition center. And models trained on them tend to degrade significantly when the setting, when you move them from a different clinic or a different scanner model. This is exactly the setting where extra shaped derived guidance would be valuable. And it's exactly the setting where it's hardest to get, because you can't collect much more annotated data, even if you want to. So the question here comes that rather than us hand designing geometric knowledge, the way we did with TTSNet, could a network learn this geometry itself directly from the training labels and still use it when those labels aren't available at test time? And this is where decode comes in. And the idea is to compute a set of shape descriptors like size of the volume, the instance sphericity, elongation from every training label using standard radiomics feature extraction. Then we use that vector of descriptors to condition the decoder of segmentation network through a modified feature-wise affine transformation applied at each decoder stage. In effect, the decoder is told at every step roughly what shape it should be producing. Now there's an obvious problem. These descriptors come from the ground truth label, which by definition isn't available at test time on new unlabeled data. So we added an auxiliary regression head that learns during training to predict that same shape embedding directly from encoder's bottleneck features. And at inference, the trained model conditions itself entirely from the image, with no access to labels or metadata of any kind. And this is the first real shift in this line of work from hand designing geometric knowledge, as in our first study, to learning it directly from data. However, it is still geometry about a single structure considered in isolation, but crucially, it's learned rather than engineered by hand. And it comes at almost no extra cost, since we are reusing information that was already sitting in the training labels. We evaluated decode on CBCT scans of the dentition on 2 independent external test centers that the model never saw during training. Decoder conditioning statistically significantly outperformed an otherwise identical unconditioned network, and did so while requiring only a fraction of the computation that larger unconditioned architectures needed to reach comparable accuracy. But my favorite result here is actually a sanity check. We built specifically to test whether the network is really using the conditioning signal rather than just tolerates it. And we constructed a synthetic benchmark where solving the task required generally combining shape and size information. And unconditioned model performed close to the chance on that benchmark. And the conditioned model approached almost ceiling accuracy on the same exact task. That's a direct confirmation that the network relies on this learned geometric signal rather than ignores it. And the takeaway from this research is that geometric knowledge about a single structure's own shape can absolutely be learned rather than hand designed, but it still says nothing about how that structure relates to its neighbors and which is exactly where our next study follows. And this is Jeopard. The third study with the same core group of collaborators was presented at MICAI, the geometry prior assisted learning for 3D tooth segmentation. Decode's shape embedding was a step forward, but it still only describes single structure in isolation of which we were calculating the shape features. But it says nothing about how the structures relate to its neighbors within a consistent anatomical layout. And for a full set of teeth, that matters a lot because segmentation errors aren't evenly distributed. The crown of the tooth is comparatively neighboring the ear, is easy to delineate, but root apices, the tips of the roots, are thin, low contrast, and highly variable in shape. and they can account for a disproportionate share of the segmentation error. And this observation was one of our findings because nobody before has signaled this problem. It could just be a small detail, except root apices are exactly what matters clinically for assessing root resorption in orthodontics. A gradual and irreversible loss of the teeth root that can result from orthodontic treatment and teeth movement. Prior attempts to bring anatomical structure into tooth segmentation encoded that knowledge as rigid rules, the neighborhood. For example, a fixed adjacency graph between neighboring teeth, and that risks overfitting to the exact topology seen in the training. And it generalizes poorly when a patient has missing or displaced teeth, which is common in practice. So the question became whether population level anatomical geometry could be encoded more softly as a statistical regularity rather than hard-coded as a fixed template. Jeopard 3D answers that by deriving a set of statistical intertooth distances from a three-dimensional statistical shape model of normal dentition. We use these distances to reweight the training loss so that the segmentation error between two anatomically distant teeth is penalized more heavily than an error between two neighboring or morphologically similar teeth. And this is a soft, distance-based penalty, not a rigid adjacency rule, which is the key difference from prior work. We combine this geometric loss term with a deep watershed instance regression branch, which models each teeth as a continuous three-dimensional energy basin and separately predicts the direction of steepest energy descent. And this combination helps the model resolve boundaries much more precisely, especially at those difficult root apices. Conceptually, this extends the geometric priors from decode, which described a single structure shape in isolation, to population level relationships between multiple structures. And please notice the pattern across these two studies. We have now moved from hand design geometry of TTSNet to two different flavors of learned geometry over anatomy. First at level of a single structure, and now at level of relationships between many structures. Both are learned from data, but they operate at different scales of the problem. We trained Jeopard on a single publicly available center and evaluated it on 4 independent external test sets, 2 in-house, which we published, and two public, none of which the model saw during training. It achieved the highest segmentation accuracy of all methods we compared against, improving the dice similarity coefficient by close to 3 percentage points, and recall by close to 10 percentage points. And those metrics were already kind of saturated because all of them were overreaching 90 degrees, 90 percentage points. And the recall of this teeth was improved by close to 10 percentage points over already the strongest anatomy aware baseline. And when we did a boundary distance analysis of the labels, the largest relative gains were concentrated exactly in the root regions, the areas that matter most clinically for assessing resorption. So the takeaway here is that encoding relationships between structures as a statistical regularity rather than hard-coded rule generalizes better to new clinics and new patients. With Jeopard, this approach only helps a model interpret an image that already contains enough information, in principle, to determine the correct answer. The input image is given, but it doesn't yet tell us what happens when the input itself is insufficient. And that's exactly another problem our final study continues and takes on. It's currently in review and has been done with Szymon Płotka, Michał Grzeszczyk, Tomasz Szczepański, and Arkadiusz Sitek. And it is XSplat, Gaussian splatting for 3D CBCT generation from a single panoramic radiograph. And every study so far I presented has assumed that the input image already contains enough information to deliver the correct answer. A full CBCT volume shows the anatomy one is trying to segment, of course, but a single panoramic X-ray does not work that way. because panoramic radiograph integrates the three-dimensional attenuation of the maxillofacial structures of jaw along curved projection ray paths into one single two-dimensional image. And that process discards that information, and no amount of additional two-dimensional training data can restore, of course, given a single acquisition per patient, can restore what's already been thrown away. This matters clinically because panoramic X-rays are cheap, fast, and routine, while CBCT is comparatively expensive and involves a higher radiation dose. It is also a lot less available in developing countries. If we could recover a CBCT-like three-dimensional volume from a single panoramic radiograph, we would unlock three-dimensional dental analysis for larger, lower-cost archives of routine panoramic imaging that already exists, the retrospective data. But this is fundamentally harder and underdetermined problem. It's geometry of acquisition process problem again, the same theme as our first study, TTSNet, but now the question isn't how to interpret an image, it's what to generate when input alone can't determine the full answer. Existing approaches to this kind of single view reconstruction problem typically represent the volume with smooth implicit field, one that isn't explicitly encouraged to align with any particular anatomical boundary. In practice, that tends to either blurring fine structures like root boundaries and the mandibular canal, or just hallucinate anatomy that input doesn't actually support. XPLAT takes a different approach. We represent the volume with learnable anisotropic three-dimensional Gaussian primitives anchored directly along the known range geometry of panoramic acquisition and predicted in a single feed-forward pass by a shared network. And here's the nice symmetry with our first study. Back then, we modeled the geometry of acquisition process by hand to generate synthetic corruption. And here we exploit the geometry of acquisition process directly using the known range paths and the simplified physics of panoramic radiography, specifically the Beer-Lambert law, as a scaffold for a learned representation. But this extra flexibility that Gaussians gave us is a double-edged sword. An explicit, spatially localized representation is more free to place density in anatomically implausible locations than a smooth implicit field would be. So we constrained it during training with a physics-consistent reprojection loss and additional simulated reprojections from viewpoints never seen at inference. And without that added supervision, increasing the model's flexibility actually increases hallucinated anatomy rather than reducing it. But when joined, they cooperate, and the representation and the supervision turns out has to work together. And XPLAT was trained entirely on synthetically paired projection and volume data without requiring any real registered panoramic to CBCT pairs, which matters because that kind of real paired data is extremely hard to collect and rarely acquired at one time. And despite that, our model recovered clinically relevant fine structures, including the mandibular canal, this thin, low-contrast structure that other baselines methods failed to reconstruct almost entirely. XPLAT also reduced average surface error over major maxillofacial structures, almost threefold, relative to the strongest baseline that didn't require oracle inputs. By oracle inputs, I mean working with complete geometry information as model's input, which is typically not available at inference. I'm talking here about oral 3D, while introducing less hallucinated anatomy in edentulous regions, I mean areas where teeth are missing. And one methodological point worth mentioning here is that these improvements were only visible once we moved our evaluation beyond conventional intensity-based metrics for reconstruction, like PSNR and SSIM, to proposed by us geometry-aware metrics that measure recovery of specific anatomical structures directly, the intensity-based metrics alone can substantially understate how structurally inadequate reconstruction really is. And the takeaway from this research is that the same geometric thinking that helped us interpret images in the earlier studies also helps constrain what a model may generate when the input alone generally can't determine the answer. XPLAT was trained entirely on synthetically paired projection and volume data without requiring any real register panel tool, which matters. And now, after XPLAT, we are stepping back and we are looking at these four studies together. The TTS used hand-designed acquisition geometry to build augmentation that's robust and that's robust to surgical artifacts and then validated across 6 centers. Decode used learned instance-level anatomy geometry as a conditioning signal, one that network generally relies on, not just tolerates. And Jeopard 3D used learned population-level anatomy geometry inside the training objective, with the largest gains landing exactly at the clinically important and hard root apices. And XPLAT used learned physically anchored acquisition geometry to recover 3-dimensional structure from a single 2-dimensional image. And these 4 studies, 4 different mechanisms and different points in the pipeline, but from broader perspective, they are centered around one idea. And whether the challenge is generalizing across clinics the model never saw, or reconstructing what a single image leaves undetermined, geometry supplies the structure that the data alone does not. And that's the common point. We give the model structure it can rely on. So it doesn't have to guess everything from scratch, from pixels alone. So let me summarize. What does this all add up to? One question runs through all our studies. Can geometry help a model to go beyond what its input alone determines? And as we saw at the start, the gap takes 2 forms. For TTTS, Decode, and Jeopard, the training data underrepresents the world the model will actually meet in real world. And geometry helps the model generalize better to scanners and clinics. It never saw. And for XPLAT, a single 2-dimensional image simply cannot fully determine a 3-dimensional volume. And there, the geometry instead constrains what the model is allowed to reconstruct, to generate. It's the same idea applied once to interpretation and once to generation. The 2 kinds of geometry over the anatomy in the image and over the acquisition process that formed it turn out to be complementary, and they can be built in any stage of the pipeline, from the training data all the way to the model's representation. And across all our 4 papers, the same thing holds. Structure geometric knowledge did what scale alone could not, or would be prohibitively costly, also not to mention rare diseases. It made models reliable outside the exact conditions they were trained on. And I'd like to stress that this is not an argument against the scale, it's a complement to it. The explicit structure alongside more data only when available, but not instead of it. And looking ahead, a few directions follow naturally from this research. The first is to learn the geometry rather than hand build it. We need to move from priors we specify by hand or borrow from anatomical atlases, as Jeopard still does, toward priors a model discovers directly from data, and we structure those priors by our prior knowledge, but we try to take this information especially from data. So it's structure from structure. And the second is to unify the 4 entry points that we proposed. So by bringing augmentation, conditioning, regularization, and representation together into a single framework rather than treating each as a separate intervention. The third is maybe the most interesting one, and it comes straight out of the XPLAT results. As we make models more flexible, and we give them higher capacity, geometric constraints become more necessary, not less. And if the models especially are to stay anchored to reality. So scaling the model and tightening the constraints goes hand in hand. And finally, the broader point, geometry guided learning is a general way of building trustworthy models wherever data is scarce and the structure is known. And that's the direction I'm most excited to keep pushing. And with that, I'd like to thank my supervisors and collaborators that are at Sano, at Warsaw University of Technology, at Jagiellonian University, and at Harvard Medical School, without whom none of this would have been possible. So thank you very much. And thank you all of you for your attention. And now I'll be happy to take your questions.
Thank you, Tomasz, for your great presentation. Do we have any questions from the audience?
Thanks for the interesting talk. So I have two questions actually, which are quite unrelated to each other. The first is, well, we typically have two eyes to do three-dimensional viewing. Is it possible to, well, you said that the radiation exposure for a panoramic X-ray is much lower than for CT. So would it help to have, let's say, kind of bifocal viewing, meaning two panoramic X-rays in order to do much better? And would you be able to determine from your studies the optimal way to take these two panoramic radiographs in order to get the maximum information, the maximum or the best 3D reconstruction? And the second question is, typically, I would assume, when I go to the dentist at least, that 95% of my teeth don't matter. So, and probably 95% of the parts of the teeth don't matter. So if you're interested in roots, probably whether the model fuses certain upper structures of the teeth is probably irrelevant. So do you structure your loss function according to these clinical use cases of particular things? And if yes, how do you do that?
Mm-hmm. Thank you for great questions. Both are very interesting. For the first one, we have to start with the dose of radiation that a single panoramic radiograph takes. So it's not actually the X-ray, the flat X-ray, as with, for example, chest X-ray. This X-ray is still ruled by a elliptical geometry that guides the X-ray source and the detector. So it's still slightly larger radiation than the X-ray alone. And I don't know how exactly are the values if we double the exposure of panoramic X-ray of those newest, lowest radiation dose devices. If we still land below CBCT scan,
way more.
I'm not sure.
Yeah, normally, well, I would wonder. So what they told me is that the current X-ray, this panoramic X-ray, is much lower than the previous one that you had in when you were going to a dentist and got an X-ray, about tenfold. So, and the normal ratio between the CT and, well, for flat X-ray is between, depending on devices, but typically they say something between 15 and 50 times. So that there should be plenty of room, more or less, for the modern CCD-based X-ray things to get a second exposure without, let's say, getting too high in radiation. So that's the question: is there something that you could optimize in that respect, making a new kind of modality a standard procedure that would be patentable and all those things? So
I suppose that clinicians would be most interesting, of course, with CBCT, which is real and which is reconstructed with algorithms that we can, which are deterministic. And there's also a field of research where with deep learning, where we reconstruct 3D volumes with self-supervised loss, with reprojection, just like it's done with deterministic algorithms. But the advantage of deep learning algorithms is that they can reconstruct almost as good as deterministic algorithm the volume not based on hundreds of projections. I mean, reconstructing CBCT with which is registered with a cone beam, but from dozens. And there are attempts to go to land below 10 projections. But this problem is called sparse projection, not single projection. And I think that this path of research can be done with collaboration of CBCT devices manufacturers, which might be interested in lowering the number of projections and not only making the dose of radiation lower per single acquisition.
Okay, no, what I meant is you said this normally CT is rare. Yeah, not everybody and not every dentist has it, but most of them have a normal X-ray. So if you would be able to have a modality that allows without a CT device to have better information than from a single panoramic thing, that's what I meant. And
okay, so you did not mean that we are using panoramic X-ray. We are just using X-ray, which is not moving. Did I understand well?
Well, I didn't know that the panoramic X-ray needed moving. I thought this was just a projection technique. So this is taken with a CT scanner, this panoramic X-ray?
There is a slide here. We can see the axial section of patient heads, and the X-ray source is rotating around 180 degrees. And throughout this movement, it registers. It's a single slice from the whole 3D geometry, but it requires movement.
Okay, so it just has no additional vertical information then.
Yeah.
So if you would take the same amount of X-rays, but would them have in a 2D, let's say, semicircle around it, so with some vertical things, but sparser, then you could go with the same amount of radiation, but may have more interesting information than just going one-dimensional.
Yeah, I think it's exploring the area between panoramic X-ray and CBCT scanner. Yes. Whether clinicians would find it useful, and we could somehow convince them and explain why is it better, then I think that construction of such device might be useful. But here I'm in this research problem, I was most concerned about leveraging the already acquisited panoramic X-rays, where the patient may come to the clinician and tell, I had 3 PXR scans throughout my history of illness, and now we can go take a CBCT if the clinician will find it necessary. But this gives some kind of useful extra information if we could visualize 3D structure based on those 2D panoramic X-rays. For example, for impacted teeth, to see how they are located within the 3D geometry.
Okay. So my second question was about, let's say, focusing on particular targets.
Yeah. And we already had an idea to create labels only of root apices and to assess the model's performance only based on those apices coverage of the segmentation. But it turned out slightly a circular problem because we couldn't very well predict and segment the areas where the roots are located. We could not autonomically create those labels. So it turned out that maybe with help of some tools, custom tools for programs like Slicer or something like that, we may make it faster, but it still will involve a clinician with annotation task, and we will need more analysis whether this annotation was performed accurately and how much it differs between scanners, etc. So we thought that we will focus on using existing metrics, and it turned out that we can. Here it is. No, I can see that I did not add the exact table with results for Gpart, but these metrics were about surface of the teeth, and we measured only the distance 1 pixel from the surface. So it turned out that when we measure dice similarity coefficient, score coefficient, we land with the value which is very driven by the large volume of the crown, and the differences, which are very, very important from the root segmentation, they are pictured in metrics values like dice of 95 versus 95.2. And this 0.2 means that the model found a lot of root apic volume. So you will miss it only looking at the dice of the whole volume. But when we assessed the recall of the volume, and then when we assessed only 1 pixel from the grand truth label, the area where root is located was took a lot more percentage weight of this whole metric. And we analyzed that these metrics are more, they better picture the whole problem. They are more sensitive towards what we wanted to achieve.
Thanks.
Thank you.
Okay, I don't see any hands raised up, so I think that it concludes our session. Thank you, Tomasz, for your presentation. It was really great. Also, thanks for the discussion.
Thank you.
And thanks everyone for attending our seminar. And we invite you for the upcoming ones as well. Thank you.
Thanks. Bye.
Thank you. Bye.